Hello class, welcome back. It's me, Professor Hunter, and today we're going to be talking about something a little bit different. We're going to be going over chapter 6, which is thermal energy and thermodynamics. All right, so up till now, we've been talking about things more like, we've been kind of been talking about like more solid things, right? Kind of like, motion, force, energy, momentum, all those kind of things, right? Kind of like, I guess I would say more massive things. So now that we've talked about all those kind of things, now we can kind of look at, you know, kind of another phenomena that we experience in day-to-day life, which is, heat, temperature, hot and cold and all that. Uh, so basically, with all the things that we've talked about up till now, we can now begin to understand things like thermal energy and thermodynamics. All right. So basically, in this lecture here, I'm just going to be going through the PowerPoint again, which is just going to be talking about temperature, absolute zero, heat, quantity of heat, the laws of thermodynamics, entropy, specific heat, thermal expansion, and expansion of water. All right. So let's get right into it then. The very first thing I'm going to discuss is temperature, right? It's a good place to start. Temperature. And temperature is something that we all have, personal experience with, whether, we step outside and it's really, really hot, we're going in a house, it's really, really cold, or vice versa. Temperature is something that we can kind of all relate to and understand. So basically, temperature is, to put it simply, it's just how hot, or how cold an object is. And of course, that's relative, right? What's hot to me may not be hot to you, and what's cold to one person may be hot to another person. So that's kind of relative. But another way we could think about temperature is with kinetic energy, right? Because, let's say, well, not let's say, we know basically objects like, this marker or this eraser is made up of little molecules on the inside of it, right? So if we were to basically heat this object up or raise the temperature of it, the molecules inside it would begin to move faster and faster. So basically what I'm saying is the hotter something is, the faster, the molecules are going to be moving in that object. So we can also think of temperature as basically the kinetic energy inside of an object, so to say, right? And so the units that we use to measure kinetic energy, well, there's two units that most people are familiar with. That is Celsius, and then there's also Fahrenheit. All right, and then there's also a third unit for temperature that we kind of use in the scientific community. That's called Kelvin, that we use the letter K for. I'll just spell it out as Kelvin. So Kelvin is probably the one you're not familiar of, but it's one we use in the scientific community for good reason, and I'll kind of describe why it's a good reason to use Kelvin in the scientific community. But let's first describe, the difference between Celsius and Fahrenheit. So basically, the units for Celsius are kind of based off of water. So let me write this out here. Let's say Celsius, Fahrenheit. Let's see if I can spell this. Fahrenheit. I think that's how you spell it. And Kelvin. Boom. And so Celsius is basically related to water. And what I mean by that is, water has a freezing point, right? So in terms of Celsius, water freezes at 0 degrees. But in terms of Fahrenheit, water freezes at 32 degrees. And then in terms of Kelvin, water freezes at 273. It's basically going to be K for Kelvin, F for Fahrenheit, and C for Celsius. And let's see, and water also boils, right? So water boils in terms of Celsius, at 100 degrees Celsius. In terms of Fahrenheit, it boils at 212 degrees Fahrenheit. And in terms of Kelvin, water boils at about 373 Kelvin. Okay, so just showing you this to kind of show you the difference between these units here, and just to kind of give it some perspective. I kind of told you, you know, from the point of view of water. So this is for water. Now these are the temperatures that water freezes and boils in these units. All right. So another thing about temperature is that temperature has no upper limit. So temperature, I'm going to use temp for short. Temp has no upper limit. Basically meaning that there's no limit to how hot something can get, right? You know, the sun that we know of is extremely hot. And then we also know the sun is not even the biggest of stars. It's rather actually small compared to some other stars. So you can kind of imagine how hot things can get, you know, if you think about how hot the sun is, and then the sun is not even that big. And think of another star that's 10 times the size of the sun, kind of imagine how hot that is, right? So basically temperature has no upper limit, but temperature does have a lower limit. So temperature, does have a lower limit that we call absolute zero. Absolute zero. So, but basically, absolute zero would be, the coldest, an object could possibly be. And I'll talk a little bit more about absolute zero, I think in the next few slides. But basically, just know absolute zero is basically like the bottom limit of how cold something can get. But the upper limit to how hot something can get, there is no upper limit. Okay. All right. So let's see here. Next, let me go over. I guess I should also say the last thing I'm saying about temperature is that temperature is also related to the thermal energy. Thermal energy, right? That makes sense. So basically, the higher the temperature is of something, then the higher the thermal energy of it is. Or another way you could think about temperature is as the average kinetic energy of the particles. The average kinetic energy of particles in that object. So basically, the higher the temperature, the higher the kinetic energy of the particles in that object, or the higher the thermal energy, right? Cool. So now that we've talked about temperature, now let's go over heat. Let me use a different color for heat. Let's use blue. So now let's go over heat. So heat and temperature is another one of those two words that we kind of use synonymously, or we use interchangeably in everyday language. But in science and physics, heat and temperature are, similar but different in kind of unique ways. Same how velocity and speed were different, but in like everyday language, you kind of use them interchangeably. Another example would be like force and impact. Probably in everyday language, you would use those interchangeably. But, in physics, these words have differences that we kind of need to be aware of. So heat basically is the flow, keyword being flow, of thermal energy, or it's the flow of temperature. I use temp for short. So heat is basically the flow of thermal energy, or the flow of temperature, right? And so I'm going to give you your first equation here. So the equation for heat, and that's going to be, we use the letter Q for heat. Again, I'm not actually sure why we use Q for heat, but we use Q to represent heat. And heat is given by M for mass, C for specific heat, which I'm going to talk about in the next few slides here, but you kind of ignore it for the moment, times the change in temperature. Or remember, this triangle is for the change in, right? So basically, this is mass times specific heat times the final temperature minus the initial temperature, right? That's basically what that triangle means. It means final minus initial, right? So this here is the equation for heat. And notice how heat is basically related to the change in temperature. This change in temperature is basically that flow of temperature that I described in the definition of heat there. And so now let me talk about the units for heat. So the units for heat are, well, they are in calories. Well, there's 3 different units for heat. I'm just going to list them all out here. It's calories. That's calories. There's joules. And joules should sound familiar, right? No, joules is basically how we measure energy, right? So joules is basically how we measure energy, basically saying that heat is a form of energy, right? So calories, joules, or calories may be another one that you're familiar with. When people, if they're watching their weight of some sort, they say, so-and-so has so many calories, right? So there's calories with a lowercase c, and then there's also calories with a capital C. Underline that for capital C, which is slightly different from the lowercase c calories. So there's a lowercase c calories that measures heat. Heat is also measured in joules, and heat is also measured in a capital C calories. Right? And so now, I guess also the last thing I want to say about heat is, since heat is the flow of thermal energy, or the flow of temperature, I should also say that heat is always going to flow from hot to cold. So heat always flows from hot to cold, right? So basically, if I have let's say I have this cup here, right? let's say this cup is really, really, really hot. It's a hot cup. And I put this cup down and I fill it with cold water. So if I fill cold water into this cup, the heat from this cup is going to flow from the cup into the cold water. So basically, we would say that if we put cold water in this hot cup, the cup is going to heat up that water. And you kind of also think of it vice versa. The cold water is going to cool down the cup, but in actuality, the cup is going to be cooling down because it's transferring some of its heat into that cold water. So when it transfers its heat over, the cup itself is losing some heat, which is why it cools down. But the heat is going to flow, or the temperature is going to flow from hot to cold. All right. So if you're looking at the slides, on slide 15, they kind of give a good example of heat. So I'm going to erase this. So we have now 2 containers of water. So this one has this much of water, this amount of water. This one has 3 times as much. So this one has 1 liter. This is 3 liters of water. If we apply the same amount of heat to both of these containers of water, well, how is the temperature going to change for both of these? So let me write out the equation too. MC delta T. So if we've ever been in a kitchen and you're boiling up some water to make some rice or whatever you're about to do, you've probably noticed if you put a big pot of water on the stove and you try to heat it up to a boil, it's going to take some time for that water to begin to boil, right? But if you put a smaller pot of water, with less water onto the stove and heat that up, it's going to come to a boil faster than what a bigger container of water would, right? So here, if I apply the same amount of heat to both of these containers of water, this one with the less water is going to heat up faster than this one with this large amount of water. So now, I think that kind of makes some sense if you've ever been in the kitchen. But let me also explain it using this equation here. So if we apply the same amount of heat, so this same Q to both of these, so let me write out that for both of them. And let me use different colors. So I'm going to use this one for red. So we apply the same amount of heat, right? So we're applying some heat to this. Let's see, delta T. And we're applying that same amount of heat to this one. Delta T. MC. So for now, again, just ignore this C here. I'm going to discuss that in the next couple slides. This is just for specific heat. But this is going to be the same for both, so you can kind of just ignore that C for now. But, so we apply the same amount of heat to both of these. So the Q is going to be the same for both. The C is going to be the same for both. Well, what's going to be different for both of these? Well, this M is for mass, right? Well, obviously, this one has more mass, and this one has less mass. And so for both of these Q's to basically be the same, and this one has more mass, basically this temperature, this change in temperature has to be less, whereas this change in temperature has to be more because this is less mass, right? So basically this mass times this temperature have to give this Q, where this mass is small and that mass is big. So let me see if I can make it more visually appealing. Let's make this letter M really big, because this one has a lot of mass to it. And so that's going to make this delta T, the change in temperature, way less. So I'm going to make it small. Whereas over here, the mass is way less, so it's smaller. And so the change in temperature here has to be bigger. And this is the case because we're applying the same basically amount of heat, or the same Q, to both scenarios. So I hope that makes sense, as far as the equation goes. I'm sure it kind of makes sense logically, but I just hope that makes sense with the equations as well. All right, so let's see. Just looking through the slides here. Oh yeah, so now let's go over the units a little bit. So I said the 3 units for heat were calorie with a lowercase c, joules, and then calories with a capital C. So if you're looking at the slides, it basically says heat is energy in transit, or basically the flow of energy, or the flow of thermal energy, right? And it defines a calorie as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 calorie is basically equal to 4.19 joules. So if we want to, so if we have basically 1 gram of water, right here, this is 1 gram of water, 1 gram of water. If we want to heat this water up by 1 degree Celsius, we basically have to we have to heat it up by 1 calorie, because that's the definition of 1 calorie. Or in other words, we have to apply 4.19 joules of energy to this 1 gram of water to heat it up by 1 degree. Okay, so I hope that makes sense. Basically just trying to describe to you, how these units work and what they're related to. They basically go back to water and how we heat up water. And then also, I guess I should also say one calorie is equal to 1,000 lowercase calories. And this is basically what we call a food calorie. So whenever you're counting calories in terms of food, you're using calorie with a capital C. So for every 1 food calorie, it's actually equal to 1,000 lowercase calories. Or you can actually put that in terms of joules by just multiplying this 1,000 by 4.19. So 1 food calorie is also equal to PHYS-1415-Ch.6 joules of energy. All right, so now let's go over, so now that we talked about temperature and heat, where we know temperature is just how hot or cold something is, measured in, Celsius, Fahrenheit, or Kelvin, and heat is actually the flow of temperature. So basically heat is something that's transferred. So I say I transfer my body heat. I don't necessarily transfer my body temperature, right? So now that we've talked about temperature and heat, let's get into the laws of thermodynamics. So the laws of thermodynamics. Dynamics. Boom. So the first law is basically one you might have heard of before. Energy cannot be created nor destroyed. Energy cannot be created nor destroyed. Right? Well, another way we can basically say this is the first law of thermodynamics. You can either say the first law of thermodynamics is energy cannot be created nor destroyed, or another way to put it is basically just the conservation of thermal energy. Boom. So basically all the first law of thermodynamics says is energy cannot be created nor destroyed, or in other words, it's the conservation of thermal energy. And another way to put it is if I apply a certain amount of heat to a system, then that system is going to have an increase in temperature equal to the amount that I apply to it. Or as they say in the slides, when heat flows to or from a system, the system gains or loses an amount of heat equal to that amount of heat transferred. So basically saying heat is transferred from one system to another system. And that's basically just energy being conserved, or the conservation of thermal energy. Or in other words, energy cannot be created nor destroyed. It can only change forms. Right? So let's see. The second law of thermodynamics, which I already kind of described it briefly a little bit, it basically just says heat travels from hot to cold. That's basically the second law of thermodynamics. In order for cold, in order for basically something to go from cold to hot, or basically to go the opposite direction, you have to do some outside work to the system. So like if you have a hot house, it's hot inside of your house, it's just not going to, become cold on its own. You have to turn on the AC, right? And the AC would be the outside external work acting on the system, forcing cold air into a hot system. But if just left alone, hot is always going to transfer into the cold. It's never going to go the other way around. And then the third law of thermodynamics is no system can reach absolute zero. Boom. So absolute zero, I described it a little bit earlier, is basically the coldest an object could possibly be, you know. So if we think of, temperature in terms of like molecules moving and shaking, the hotter something gets, the faster molecules will begin to move. Well, vice versa, the colder something gets, the slower, molecules will begin to move. So when something is at absolute zero, that means the particles are so cold that they're just basically still, like not moving at all. They're just completely still. And I know we tend to think, like molecules inside of, say, this eraser here are pretty still, right? But even the molecules inside of this solid object have a little bit of motion to them, even though we can't feel or see it. And it's solid, it doesn't actually feel like it. The molecules actually are moving just a little bit. So the third law of thermodynamics basically says no system can reach absolute zero. So basically in nature, in the universe, there's nowhere in the universe that is absolute zero. We do have labs and places where people do experiments where they cool things down to very, 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 very close to absolute zero, but there's no way we can reach absolute complete zero, right? I may post a video about that. It's kind of interesting. But anyway, these are the three laws of thermodynamics. First one being the conservation of energy. The second one being, heat transfers from hot to cold. And the third one being no temperature can reach absolute zero. All right. So let's see now. Let's go over entropy. Entropy. Boom. And so entropy, if you haven't heard of it, is basically a measure of disorder of a system. So entropy is the measure of disorder. So whenever you think of entropy or hear entropy, you can just go ahead and think about disorder. And basically, I'm bringing this up because all systems will tend to go towards disorder. So if you have a system that was once in order, it's always going to go or, basically approach disorder as time goes on, right? So an easy example of this would be, let's say your room, right? If you don't clean your room, let's say you clean your room one day, at the beginning of the month, and by the end of the month, if you don't do anything, just go about your day-to-day life, you don't clean your room, you don't try to reestablish order in any kind of way, your room is going to slowly and slowly, descend into disorder over time. That's if, you don't clean your room or do anything else. You cleaning your room would be, you being the external force, acting on the system, which being your room, putting it back in order again. But if we were to just leave things as they are, things will always tend to go towards disorder. So entropy will always increase with time, unless there's some external factors happening, right? All right, so I think that makes sense. Let's see here. Boom, boom, boom. All right, so now Now let me talk a little bit about specific heat. Specific heat or specific heat capacity. And let me give you this heat equation again. This letter C right here is actually the specific heat capacity for C. So that's what that C represents. This C represents specific heat capacity. Well, the specific heat capacity, well, describe it in words, is basically just the heat required to change the temperature of a substance. Boom. So specific heat, or this C, is basically just the heat required to change the temperature of a substance. You can also kind of think of this as, thermal inertia, right? And it's kind of like inertia, because we know inertia was the resistance of an object to change state, right? So specific heat is basically the resistance of an object to change its temperature. And this C is basically different for different substances, say water or oil, or, steel or iron or gold, all different kind of substances. This C is going to be different for each one. So basically, now, hope if that makes sense, let me just write this over here. If we have a high C, or a high specific heat, then a lot of heat is required. A lot of heat is needed, I'll say, to change the temperature. So if the specific heat is high, then a high temperature is needed to basically change the temperature of that object. So let me just give you an example of the specific heat of a few things. So the specific heat for water is about 1,000 calories per kilogram per Celsius. So pretty high. The specific heat for silver is 56 calories per kilogram Celsius. So notice the difference here. Basically, this says in order to raise the temperature of water, which is 1,000, a lot more heat is required. A lot more heat is needed to raise the temperature of water versus something like silver. So a good example of this would be like if I took a cup of water, take it outside and just set it out there, and next to that cup of water, I take a piece of foil, aluminum, and I set it next to the cup of water. If I leave both of those objects outside for, an hour or so on a hot day, and then you go back out there and check on it, if you touch the foil is going to be hotter than if you put your finger in the water, right? And that's because the foil probably has it's probably not silver, but aluminum has a lower specific heat than water. Water has a very, very, very high specific heat. And so that water, the change in temperature of the water won't be as much as that foil because water has a high specific heat. So because it has a high specific heat, a lot of heat is needed to change the temperature. And same vice versa, if the specific heat is lower, so if it's lower like silver, then not as much heat is needed to change the temperature of it. All right, hope that makes sense. So let's see here. So we talked about entropy, we talked about specific heat. Now let's go over thermal expansion. So now I'm gonna go over thermal expansion. So thermal expansion basically just means if you raise the temperature of an object, basically that object will begin to expand. So if we raise the temperature of an object, it will expand, right? And the equation for thermal expansion is gonna be, delta L is equal to alpha L delta T, right? Where this delta L here is basically the length of an object. So let's say I have just a steel rod here. Just a steel rod. And this steel rod has some length. So boom, some length L. So this L is for the length, the original length of that rod. And this delta T basically here is the change in temperature. And so if we basically raise the temperature of this rod, that would be the change in temperature of it. And so if I were to get like a lighter or something, or put this rod in a flame and change the temperature of it, it's basically going to begin to expand outwards. Now, why is it going to expand outwards? Well, basically, it's going to expand because this rod is made up of tiny molecules, right? And if we increase the temperature, then the molecules will begin to basically shake and vibrate and bounce around in this rod a lot more. And so if we raise the temperature enough, the molecules actually bounce so much that will actually make the rod expand outwards by just a little bit. Not like, a lot, but, enough to where there's a noticeable difference if you go out of your way to measure it. But you probably can't tell with the naked eye that it expands. But you'll probably notice that this rod will bend or distort in some kind of way. Yeah, and so this delta L is basically how much it's going to expand after we heat it up. So you can kind of think of after we heat up this rod here, let's say it expands this much. Boom. This right here is the delta L. So that small amount here is the delta L, or is that value, where this L is the original length of the rod before we change the temperature. Okay. And then the same also happens vice versa. If we were to cool down this rod, then it's actually going to contract a little bit. All right. So I hope that makes sense. So now the last thing I'm gonna talk about is the expansion of water. So thermal expansion, this notion that objects expand when the temperature increases and contract when they decrease. That's true for most objects and most substances, but it's actually not true for water. Well, it is true that if you heat it up, it expands, but it's actually not true that once you freeze water, it gets more and more dense, right? Because basically what I just said was if you increase the temperature, an object expands outwards. So if it expands outwards, it becomes less dense. And so if something gets colder, it should get more dense. So the molecules should get closer together when something gets colder. But water is actually more dense. So ice, I should say this, ice is more dense than water. Less dense, I mean. Less dense. All right. Yeah, so water or ice is basically less dense than water. Well, sorry about that. So let me see if I can try to explain this less dense than water and kind of what this basically means. So you can kind of imagine if we have a cup here, and this cup has like different things inside of it. All right, different kind of fluids. So this fluid that's on the bottom, right? So we got like some drink, we mix up 3 different things inside of it, like water, oil, and something else like vinegar or something. Things that don't mix. If we, put all those things in a container, they're basically going to stratify or, section off something like this. And we know whatever is at the bottom is going to be the most dense, right? And then whatever is at the top is the least dense, which is why, it went up to the top, and whatever is most dense goes to the bottom. All right, so now how does this relate to the water and ice thing? Well, we know if we have a cup of water, and we put some ice in it, we know that ice is going to float in that water. Well, why is this ice going to float in the water? Well, the ice is going to float in this water because it's less dense. The ice is less dense than the water, so it's going to float in the water. And it's kind of amazing if you think about it, because as things get colder, you would think they become more and more dense, or they contract, right? But water, because water is structured, and so it becomes less dense because it's structured. This is due to the structure. I'm going to say structured. Structured. I hope I spelled that right. I think I spelled it wrong. You know what I mean? Structured. But basically because water has a crystalline shape. Yeah, let me say... structured. I think I spelled it right. So basically, ice is less dense because it's structured. So ice is more or less dense. Oh wait, that's not right. I don't know why I wrote that. Ice is less dense than water. There we go. Writing too fast. So ice is less dense than water, and that's because ice is structured in such a way that it expands once it freezes, hence causing it to float upwards. All right. So, yeah, that's pretty much it for this video. It's a little bit shorter than the others, but you know, I hope I got the point across. After watching this video, you should be good to go with your homework and quizzes, hopefully. You know, if not, just kind of look through the chapter a little bit more if some of what I described or talked about was not clearly understood. And yeah, that's it. Good luck.